talk about your project. We can start from the first group, Ladislav and Martin.
But maybe let's wait Yaroslav.
Okay, we can start for the second group. Abdulaziz and Fatima. After that, who will be the candidate? Yeah, okay.
That will be the next one then.
Yeah. I will talk about the HDR, high dynamic range. Project unit, laptop, this.
more like than low dynamic range, but you can see the whole data like properly, and it doesn't have the data in every like pixel of it. So it's different from the high dynamic range, and we are like measuring the high dynamic range with this exposure value, and for photography they are using like spots for this term. And this is the first high dynamic range image, like it's in around like 19th. The first time high dynamic range term has been used. And why high dynamic range? Probably like you will choose the better performance, better like looking photographs for your, I don't know, anything like. And that's why high dynamic range is like important, like to see the images like with to see the screens that you have in your photos in better resolution. How is it working? So first, photographers take the pictures of like of the same screen with different like exposures, like with like exposed for the back points, black points, like dark point areas, and also with the high dynamic, like with the bright areas, and then they compress those images together and they get the high dynamic range. So this is the example of it. And high dynamic range is used also for not just colorful images, also it's used for the black and white images. So you can see much more details in high dynamic range than with usual stuff. This is a picture that your mind is working differently with the comparison with the others. Like some of you probably is like seeing this dot, and the others are like looking and see the bird in here. So this is all about the light in the images that we are comparing. And let's see, like when you look at this picture, you will probably say that the squares that in A and B are totally different, and like colors are different. But in that case, that I will show you that those are the same, you will probably like understand that those are the same images, but they are like different with the light. This is also another example. Like you can see that you can first say that those are the different colors, but this is the same color, but bright. They are different from the light effect. Also, like with the comparison the other square, you would first say that okay, this is the white color, but this time, like you will say that okay, this is brighter, and always depends on like the lights that affects your eyes. And in the real world, like dynamic range is like really changing from higher points that our eyes can't even see. So our eyes like is like limited to see some kind of dynamic range, and this is the dynamic range that 400 nanometer and 700 nanometer that we can see. And with the low dynamic ranges, it's like changing around like 100 nanometers. So in the low dynamic range, so what we want to see is that compressing that data to those that we can see properly with our eyes, so we can see it in the monitors. This is the bit difference, like how does it change? It doesn't look good in here and so forth. limited, but for high dynamic ranges, it's like we can take like any kind of range we want, and there's no like limitation there. And these are some encodings to something like Microsoft, for example, use this sRGB like power encoding. And we are mostly using HDR and XR, like OpenXR, the encodings because they are like can be seen anywhere, and there is no limitation for like you should see it in this monitor, but we can see and use it everywhere. What's tone mapping is? Tone mapping is the operation that we are dealing with. Like currently, the high dynamic ranges are mapped to low dynamic ranges with these tone mapping operators. There are like a lot of kind of operators that around more than probably 100. So we are at every tone mapping is different with the others. Like some of them is comparing global and compared to the global tone mapping, and some of them are like compared to the local tone mapping operators. Why does it differ? Like global tone mapping operators are fast processing, and they are like using but with these global mappings we are losing details, but for local tone mappings it looks nice, but we can have like some halo effects that might be look like this. And the linear tone mapping operator, so the left side is usual HDR image, but if we would have like high dynamic range monitor, then we could see it like this. But this is the low dynamic image that mapped from high dynamic range to low dynamic range. And those are some examples. Those are references.
Thank you for your presentation. I know about your project in detail, but can you please explain that what you want to do in this topic?
This is also my like thesis topic. We are going to probably develop we are developing like tone mapping operator. But right now I'm doing statistical analysis for like all of the tone mapping operators that are there. So like we are going to calculate each of the images, and we are going to use subjects to give the feedback about each tone mapping, which one is better than other, or like which one is like more realistic than the others. Like we are doing some kind of measuring to see which one is better to use.
It means that at the end you will generate a novel method or technology.
Hopefully.
Yeah. What's the challenge that you are facing in this area?
Challenges is like I might like a picture better, and someone else would like it in some kind of different way. So everyone is like looking at the pictures like different way, and like tastes are different. That's another point. And another big problem is that we don't have monitors like high dynamic range, so we can see the data that we are dealing with. So it's the main
problem. Okay, thank you so much for your presentation. Other people, if you have any question, you can ask here. Okay.
Okay, I can do next.
Okay. Do you have a pen? No, I don't. Rick, do you have a pen?
Do you have a regular DJ tape with yours? Hey everybody, my name is Kristaps and I'm gonna tell you a bit about our team's progress with super resolution imaging. So what is super resolution imaging? Well, basically it's the process of combining multiple bad photos, so photos of bad resolution, and to get in the end a photo with a better resolution. And hence the name super resolution. And if you can't imagine this, then think about CSI. Think about the CSI, the button enhance. And motivation behind super resolution is that people always want more and better. Like, for example, we have a satellite orbiting some planet or object, and it's been orbiting for a few years maybe. The camera is pretty outdated, but we still want to do some other fancy stuff with the images that we get. So what can we do about it? Well, we can use super resolution to make the images look better. Oops, sorry.
Hang in there.
So you will
He's
be
lying.
able to see what super resolution is.
About what? I don't know.
So what do we know?
That at 9:15, Ray Santoya was at the ATM,
The question is, what was he doing at 9:16?
shooting the 9mm at something. Maybe he saw the sniper.
Or was working with it?
Wait. Go back one.
What do you
They have
say?
such an amazing tools, you know, these CSI guys. The software is brilliant.
Bring his face up. Full screen.
His glasses.
There's a reflection.
Of course there is. There's always reflections. So he's super resolute.
It's in Mavita's baseball team. That's
A lot.
another one.
And he's talking to whoever's wearing that
Of
jacket.
course, it's not as dramatic
Yeah.
in real life, but we're getting closer, you know. So the process of super resolution consists of basically three parts. The first one is the image acquisition, which is, as you can imagine, taking photographs. Well, usually it's not taking photographs as in just going around and photographing stuff. It's mostly videotaping moving stuff. Because if we take identical images and try to super resolute, then nothing will happen because they have to be different so that we could extract the artifacts that we actually need from the image to make it better. The second is image registration, which is the process of aligning two or more of these images of the same scene. So we have, for example, some moving stuff in the frame, and we take parts of them and arrange them like geographically so that it would make sense. And the third part is image reconstruction, which is combining the multiple unidentical images back together to make the final image. So what has been done in the project? Well, we have gathered the information, we have researched the freely available software solutions, we have found some, although there are many commercial ones, which you have to license to get your hands on, because it's quite a profitable thing, as it turns out. For some reason, people want to find out who killed who. So, and we have understood the basic principles of how it works, and now we need to gain a deeper understanding of the underlying principles, deeper understanding of the code, so we have to read through the code that we have found, which is open source, written in Python. And we have to try to apply the methods, the algorithms that are presented in the solutions that we could find and to compare and analyze the results. I mean, this is super resolution. It's not very trivial. It's not in a matter of 3 or 6 credit points. People are writing doctoral theses to implement that, so we're probably not going to be able to write something novel, especially when guys writing doctoral theses actually say that most of the new methods rely on the methods written in like the previous century, so it's more like tweaking stuff and making it look a little bit better, something like that. And yes, we also need to do the actual deliverable, which is the poster. Schedule, so this is how our plan looks right now. Yeah, it fits into the time frame, so we're good. We're good. And thank you.
Do you have any question?
No, it's a genetic freak.
Yeah.
You see the reference with image processing here?
Can you please go to your second slide? Yeah. The thing that you mentioned in your presentation was fully true, but in the image super resolution, we have two approaches. Multiple image super resolution, that was that thing that you mentioned in your presentation, and another one is the single image super resolution, that at the beginning we just have one low resolution image and we have to enhance the resolution or super resolve the resolution of them. Most of the super resolution algorithm that works for the multiple images use registration, as you mentioned in that case, and usually used for the medical image processing. It means that people in this area will use a lot from the registration techniques, and from people that work with the satellite images or remote sensing images, because they got lots of image, for example, of the field, and they have
camera
to,
is bad,
and they have to combine them to generate a new resolution. But for the single image, we don't use registration because we just have one image.
Okay. Honestly, I didn't know there is such a thing as a single image super resolution.
And in that case that we have some shift in our image, it will be better if we use some multiple image super resolution. But if we don't have any shift or any movement in the image, it will be better that we use some single image super resolution. But although that if we want to divide it, the single image or multiple image, we can divide it to two categories, frequency domain and spatial domain or something like this, but we don't talk about this. My suggestion to you, because as I see that you didn't start to work on this area, you have to plan to start from 24th, from your schedule, 26th of the April. My suggestion is that instead of working on the multiple image super resolution, working on the single image super resolution, because it's easier for people that really knows a little about the image processing. A little not means that.
Okay, so that was like originally that was the idea.
Yeah.
Okay.
And there are lots of images. The simplest way that we don't call it super resolution, but the simplest way for upsampling image is interpolation. And most of the single image interpolation, single image super resolution use this interpolation. Doesn't matter, SP-line, bicubic or something like this. And after that, they will retrieve some high frequency that missed by interpolation. My suggestion to you is work on that area instead of working on multiple image, because for the multiple image, first you have to know how single image super resolution work, and after that, by that background, come to the multiple image super resolution and add registration to this. But
Okay.
it's up to you. If you want, you can work on the multiple image super resolution.
Okay, thank you.
You're welcome.
Can I go next?
Yes.
Hey, I'm Henrik, and I don't have slides with me, but what I'm going to talk to you about is backing image compression for satellite images. So the problems or the complications with satellite images is that we can't just use the algorithms used on board computers because they are too slow to be used on the processors, at least some of them. So my aim is to find the best algorithm currently in use for satellites or for computers that would work well for our microcontroller. So basically, the ideal case would be if the packing algorithm would be progressive. So first, when you download down the data from space, you want to estimate how good the image is. Do you want to save the image? Do you want to download the image fully? So it has to be progressive, lossy to lossless compression. So the more you download from the picture, the more information you basically get to make the resolution better, or to basically make the resolution better. There are some different ways to do it. The simplest way is to just only download some of the pixels, maybe every 8th pixel, for example, or something like that. So the main thing that we are picturing is the Earth. So it's Earth observation, which means that the data on the images is very specific and very different from, for example, human face pictures, which means that the algorithms that compress human faces and things like that very well aren't necessarily the best ones for Earth observation. So what's the satellite images that I work on are SQ1's images right now, and the software will then go on ESEO, European Student Earth Orbiter. The complications there are that the camera sensor itself gives out raw data, so it's bi-array, which is an image filter, and the data itself is 10 to 12 bits different in those two cases. So one of the complications is how to convert it to 8 bits or 16 bits data the best, so it would be compressible in a good way. What I've currently looked at is just for starters implement JPEG LS and compare how fast it would run, right? Because the current algorithm that was used was just based on regular data compression, not image compression, and its speed was too slow. So first I'll try to try the algorithm in MATLAB, then write it in C and try it on the microprocessor and see what the speed is. If it's not good enough, then research other pre-processing techniques, try them first, and later on just try maybe a different algorithm. Currently I'm doing literature research if I can find some very good article that already has these things analyzed, but haven't found any really good ones yet. Yeah, that's about it. Any questions?
You have any question? Which type of image compression you have to plan to use? Lossy or lossless?
Basically, initially I'll try lossless, to do separate ones, lossy and lossless ones. So just because we need basically both. We need lossy to estimate how good the picture is, to want to download it fully, and lossless because there isn't really that much information. We need all the information that we can get from the space. So that's why usually satellite images, if you have the bandwidth capabilities, they are downloaded lossless. If you don't have the capability, then you do lossy compression. But usually
But
there's
you
some scientific data in the.
But you have to be careful about the lossy methods that you use, because if you, for example, lost some part of the image, maybe lost some stars or some planet or something like this.
So the question is what the application is for these specific satellites. For SQ1, the main reason why to have a camera was PR and to have nice images. So if the aim is to have nice images, then you can have basically a lossy compression, because the lossy compression basically it reduces the information that we don't value in a picture, basically, when we just look at the pictures. And the SAO has basically also a PR goal specifically, but we ourselves want lossless pictures, so so that's why we are gonna look at both. So it's current algorithms are JPEG and JPEG LS, which is JPEG lossless. Yeah, that's there's a couple of other algorithms, but most of them don't describe the full process right now. Yeah, hopefully I'll find something better also.
Okay. Yeah, any question? People? No? Thank you.
We can go next. It's one person or two? You can go both. Huh? We don't have slides anymore.
So, hello everyone. Our project topic is 3D image construction from multiple 2D images, and we are using Kinect sensor. So basically, the Kinect sensor gives us the depth image. So we take multiple images from an object which is rotating, and using these pictures, we can construct the 3D model of the thing. And basically, we have divided our work into 5 major steps. First is reading the images. This includes the camera calibration, so that we could know how big is the object in real life. We can do it using chessboard picture. Then we have to filter the data, firstly using simply threshold, just to get the read of the background and the foreground, and then we have to apply the bilateral filter to smooth out the errors. Thirdly, we have to calculate the transformation matrix, which transforms the depth of picture pixels into the right position in the point cloud, and this way basically after that we have the point cloud, and then we can use interpolation to create surfaces, and then we have the model basically.
And the main purpose is to make like 3D scanner, so out of that we can then 3D print this object which is scanned.
And what we have done already, we have done some research in the project. We have wrote code to apply the bandpass filter and also the bilateral filter.